Dr. Lee Kalcsits is an Associate Professor of Tree Fruit Physiology in the Department of Horticulture at the Washington State University Tree Fruit Research and Extension Center in Wenatchee, Washington, US of A. He serves as the Endowed Chair of Tree Fruit Environmental Physiology and Management. His research programs works towards developing and integrating new approach for solving physiology-related questions that will positively impact the tree fruit industry. Dr. Kalcsits, welcome to South Africa. We look forward to your talk, and I would like also to thank you for always inviting us South Africans to Wenatchee. A lot of us have been there quite a number of times, and you always make it a good time for us there. We really appreciate that. You're welcome to come and give your talk.
All right, good morning. So first of all, I'd just like to thank HortGrow for the opportunity to come share and exchange ideas on the research that we do in Washington State and the opportunity to learn about the differences between how we grow fruit in Washington, USA versus here. It's a very different environment. I spent last week touring orchards and seeing how different the climate is here and understanding the challenges that you face. So for the first talk I'm going to give is on this Smart Orchard project that had started in 2019. It was in response to industry demand and kind of them feeling overwhelmed on the amount of new technology that was coming forward and flooding the industry with new data, new images, new options for managing water, different ways of doing things, and there's so many different companies, so many different software platforms, so many different ways of doing things that they wanted a filter, a way for kind of an unbiased evaluation of some of those new technologies to then provide a stepping stone to improve the success, improve the adoption, and reduce the risk for growers adopting those technologies. That's kind of why this project started up. I came in the second year, so the title of this talk is Smart Orchard 2.0. There was a first year site that was started in 2020 during COVID. It was in response, or part of the Washington Tree Fruit Research Commission, and also several different collaborators, which I'll introduce in the next slide. And then I came in working on the plant-based sensors. So some of this talk, I'll kind of introduce some of what the other people are doing on the project, and then I'll talk about the plant-based side of things, the plant-based sensors for irrigation management as what I'm going to introduce. So this project has kind of 5 key team members. One being Bernardita Salato, so she's a tree fruit extension specialist, so our outreach, one of the big outreach people within the university system. Steve Mantle is the CEO of Innovate Ag. He's really a data guy. His whole effort is looking at spatial mapping. They've partnered with Green Atlas, which is a imaging company, and then the other side is data integration and connectivity. So they're dealing with we have areas in the States where we have very poor cell phone connectivity and data connectivity. So a lot of these sensors have connectivity where it delivers data to your smartphone or your computer systems, and connectivity can be an issue in some of those sites. And then also the data integration. So working across multiple software platforms and bringing it all together into one place where all the data gets integrated, and providing a platform for growers to view that data. Like I said, I'm focused on the plant-based sensors. I'm a physiologist. Troy Peters, who's an irrigation engineer, so he does a lot of work with the irrigation systems and optimizing those. And then Lav Cote, who's a remote sensing agricultural engineer, so he does unmanned aerial vehicles, so UAVs, drones, and a lot of satellite imaging. And really, this is a industry-university partnership. So we have the growers, and we work in grower orchards. This isn't just purely a research-based project. The funding comes from the Washington Tree Fruit Research Commission, which is much like HortGrow. And then we have also partnered with a lot of the sensor companies. So really the idea is that this is going to be a test bed for new industry or new technologies coming in. So if a company wants to put their product against things that are tried and true and tested, this is the place to do it. It's a way to really compare apples to apples. You can't compare one technology in this orchard and another technology in another orchard. That's very difficult to do. So we're bringing it all together. So we've actually partnered with a lot of these technology companies. They brought their sensors, they brought their imaging approaches or their mapping approaches into this smart orchard as a way to evaluate new technologies. So this is just a 4-minute video summarizing what the project is all about. So this is a field visit to Washington State last year.
The way that we do things is the same way that we've been doing things for over probably 100 years.
40% of all the food that anyone produces is going to waste. When you're out here, specifically in Honeycrisp, you see like apples on the ground that you're not picking. They're low quality fruit.
We haven't been very technology oriented.
We always plan on next season we'll do this and then next season we'll do that, but sometimes we can't complete the puzzle because we don't have the information when we need it.
So today we are at Washington Fruit's Grandview Ranch, and we are kicking off the Smart Orchard Project, site number 2, and brought together researchers from Washington State University to select sites within a Honeycrisp block to determine where best to put groupings of sensors. There are a ton of pressures on growers and frankly on the environment as it is today.
We are inundated with data. There are sensors everywhere. The challenge is to make sense of this data.
Growers have really struggled with data silos. Some growers are seeing as many as 19 different apps as they look to make decisions. It's really hard, if not impossible, to interrelate those data points and align them around economic impact for the grower. And that's really part of our focus here as part of the Smart Orchard project.
We're trying to figure out what's the most cost-effective way to put sensors out in the field. If it doesn't provide value back to the farmer, then what's the use of buying a $10,000 sensor?
The scientific information need to be converted to some technology or some product, and I think this project allows us to do that, and that's the fun part.
There are people with different skill sets. Soil scientists, we have data scientists, we have engineers. I'm a tree physiologist. There's the industry side of it, the horticulturalists that come on board and speak to industry needs.
Part of what we're bringing together is a mobile ag data center where we process that data from imagery on site.
We take images of crops and we can detect stressors, disease, physiological states to help growers make better decisions about what they need to do with their crops. We are actually, donating our technology in kind in order to help forward this research.
That is one of the technologies that we want to assess. It's very common in row crops to assess the variability of the soil in terms of the chemistry.
This is a C-cell battery on this, and it'll transmit soil moisture content for 10 years. So it changes how you resource getting data out of the field.
My program, research and extension program, is focused on developing and promoting crop monitoring and management technologies for the fruit crops and some other high-value crops.
Innovate Ag is one of the leaders moving the ag tech forward in that it really does one of the better jobs of bringing together disparate data sets. That includes data sets from different sensor providers, coalescing those into one easily accessible source.
We have been entrusted by the growers of Washington to help them find innovative solutions to keep their operations profitable and sustainable into the future. So this is how we see ourselves leading this effort, by spearheading things like the Smart Orchard.
So that kind of gives an overview of what we've been doing on the project, some of the key things that we're focused on. I'm going to kind of break some of that down into where we've seen success and where some of those options might be. Going back to, there we go. Going back to the original Smart Orchard, so it was a Gala site. It was a Gala block in its 7th leaf, and getting into full production, and it was a perfectly flat site, so there's no variability. And you can see that. These are spatial maps of bloom. How do I do that again? Can you go back to that slide? There we go. Now, on the left is 1 year, and on the right is another year. You can see even for Gala, it's biennial. In general, the bloom counts, even on the left, were high enough for full crop load. So we had, Ken was talking earlier in the morning session about excess flowers. We generally had 2, 3, 4 times the amount of bloom needed to produce a good Gala crop. So, this was an ideal site to explore spatial variability, to explore some of those mapping technologies, but nonetheless, they kind of fine-tuned some of their approaches, did a lot of ground truthing to be able to very rapidly map bloom counts, so they can go in at bloom time, get an idea of the spatial variability of bloom, clusters per tree, where that variability might be, and allow growers to target, especially when they're hand thinning or hand bloom thinning, their target areas where there might be exceptionally heavy crop loads. Going into the Smart Orchard 2.0, it was a Honeycrisp block, so Honeycrisp was much more problematic than Gala, and it was spatially variable. So we'll go into that. So working kind of on the soil side was Bernardita Salato and Lav Coat, and they worked at combining drone imaging, so above the canopy variability, looking at electroconductivity mapping. I think that's pretty common in a lot of orchard environments now. There's this new technology called soil optics, where they are looking at individual nutrition mapping. So looking at potassium, magnesium, and calcium concentrations in the soil. They produce these spatial maps that correlate reasonably well with lab analysis. So you're not just going out and grid sampling. For soil analysis, you're getting a spatial map of relative variability in those nutrient concentrations. So it helps kind of fine tune, especially in highly variable blocks, helps optimize nutrients right from at planting, and then you could do that year to year as well. And then we combine that with our USDA soil survey data, so we have maps of soils that go down to the individual block level. It is jumpy. There we go. All right. So this is the 2.0 block, the second block. So it's Honeycrisp. It's an older block, kind of medium density. On the left, you can see this is the type of variability we see. That is, that's the electroconductivity. So we get really high conductivity in some spots that affects plant growth. That tends to relate to water holding capacity as well, and organic matter. The green area on the top left, that is a kind of a low vigor area, and then the red down at the bottom gets a lot of water, and we have excess vigor that creates a lot of problems. So there's a lot of variability in the block. The trees are exceptionally small in the low vigor area. They have a third to half the productivity as the lower block, but they produce higher quality fruit with less bitter pit. So it's really about finding that balance and determining whether it's reasonable to optimize that variability. But this is the type of maps that we produce to explore the variability, to figure out where to really dig down. We use these maps and then identify high vigor, low vigor areas with different soil characteristics. And so this is a blown up version of the conductivity mapping where we have these key sites that we then provide. Rather than looking at the spatial variability, now we're looking at sensors. We're looking at infrared sensors. We're looking at plant-based sensors. We put a lot of soil moisture sensors, and it's not just the different technologies, the different ways of measuring soil moisture, but it's also the different software platforms that are used, and allow and expose growers to those different software platforms and how they use them, or how easy they are to use to manage their water and understand their variability better. Again, here you can see kind of layers of data. And again, the Innovate is the company that integrates all this data together into one platform that allows us to understand those relationships better. So a grower that uses a universal platform can take all their data, put it all into this one platform and use that data. Much easier than if they had 5 different software platforms. It's in 5 different apps. They're moving between apps to try and decide, what they want to do or how they want to manage their water. So we have, I keep pressing the wrong button. I keep wanting to press the lasers. There we go. We have, this is, again, going into the remote sensing. We have the difference, again, a lot of spatial variability within the block. But we have NDVI, which is just a greenness index. We have, during the summertime, we've put drones up to look at temperature, looking at using infrared sensors to identify variability in canopy temperature in response to evaporative cooling practices that we use in Washington State to reduce sunburn, and also to just understand the overall risk to different parts of the block, because that lower vigor part of the block is much more susceptible to sunburn than the higher vigor area where the canopy is more enclosed. And another thing that Lav, the engineer, is doing that does the remote sensing is evapotranspiration maps. So it allows us to actually assess spatial variability in water use. And so not just understanding soil water holding capacity or soil characteristics that hold water, but also understanding how differently the trees use water. And when you put those two together, it really helps change how you view irrigation management. But again, these maps are really nice. They produce really nice images. But then when you start to break it down to, well, what's a management unit? Then it becomes a challenge, because so lower part of each of that field, do you break that apart, and how do you manage that differently? How do you make a decision? And then is it worthwhile to do that? Because if you only put one sensor in one place in the block, it's really difficult to manage 2 different locations. You split it apart. So I kind of have the rule that if your management unit is your orchard block, there's no point in putting more than one sensor. You just have to place it in that medium location. If you want to split that block apart into different management units to optimize vigor or to optimize fruit size or different things, then you need multiple sensors, and then it becomes much more expensive. You need to look at that cost to make sure that that is effective for those decisions that you're making. So this is the relationship between the traditional way of measuring evapotranspiration and then evapotranspiration measured with drone imaging. So they've done a really nice job at developing these models for assessing water use variability within the orchard. They can do it on the top left. This is satellite based, so it's 30 meters per pixel. So very low resolution. You're getting multiple trees or multiple areas of the block within one little pixel image. But the drone is 7 centimeters per pixel. So you're looking at basically leaf level variation in evapotranspiration. So what I'm doing is really led by Victor Blanco. He's my postdoc. He's been working in my lab since we started this project in 2020. And really the focus is to get at some of the effectiveness or reliability of plant-based sensors. So when I say plant-based sensors, I'm talking about sensors that are installed on the plant to monitor, it could be monitoring fruit growth or trunk growth or stem water potential or sap flow. So there's a lot of new sensors on the market that are and more every 6 months there seems to be a new one that's coming out on the market that measures water use or measures plant water status or basically does something to help irrigation. So we're just getting into this. We're evaluating just dendrometers and then measuring stem water potential in real time using this chip sensor right in the middle here. So it's a microchip sensor that gets installed into the trunk, and it's a little pressure transducer on the chip that measures stem water potential in real time. So the traditional way of doing that is you go out with a pressure chamber and you look at the stem water potential midday, but this gives us real-time data throughout the day. So we get pre-dawn measurements, we get midday measurements, and then we get the recovery rates and some different traits that we can look at with those sensors. So this is kind of the output of those microtensiometers or those fluoropulse sensors, the chip that we insert into the tree. The X's are the red X's at the top. That's where we've gone out and measured with a pressure chamber. So we have a lot of pressure chamber measurements, the traditional way of measuring stem water potential through the day. So you see this daily variation where it recovers at night. So you see it go up, and then it comes down, and you get a lower midday stem water potential. And the hotter it is, and or the drier your orchard is, the more negative that will be. So more negative values indicate more stress. And this is the type of output we get. So instead of getting just that X, where we go with a pressure chamber, we're getting this continuous data throughout the day. And you can see the sensitivity of it by, we see the slight plant recovery during irrigation events during the midday. So you see these slight increases. So rather than getting a very rapid decrease in a minimum that's if you don't water the whole day, it's gonna peak down and then recover back up at night. You can control that by pulsing irrigation during the day, and you have stem water potential that doesn't go down as far. And when it doesn't do that, you actually get better fruit growth, because when stem water potential drops too far, fruit growth stops. And we see that in really hot days, that even if soil moisture is good, you're at 90% or 95% of field capacity, that fruit growth will stop even if all the water conditions are good, because that stem water potential drops. So this is looking at, this is in apple trees on GA90 rootstock. We measure stem water potential at several different points during the season and compared it to the microtensiometer readings. So the microtensiometer is on the left, going upwards. The pressure chamber's on the right, going across the bottom. And you can see there's a really nice relationship between that. And that line is a one-to-one relationship. So we're getting really reliable measurements of stem water potential in real time throughout the day. So it's very promising. We're going into our second year of measurements right now. It's not the cheapest, but it's the technology is, the cost is in line with other irrigation management sensors that are already on the market. We have fruit and stem dendrometers that we installed on the exact same trees. So we wanted to pick those locations of high and low vigor and then over-install sensors on a few trees, because we wanted to get those layers of data that help explore the relationships. So we have the microtensiometers, we have sap flow sensors. I won't show that data here, but we have it. And then we have these fruit and stem dendrometers. And what they measure is very similar to stem water potential. You get this daily variation, very small retraction and expansion of a trunk. So during the day, when it gets hot, the trunk will shrink. It's like when you suck on a straw, you get tension that pulls that straw in. It's the same thing that happens in a tree. And then at nighttime, that pull stops, So then the straw relaxes, and then it comes back out. So you get these small amounts of variation in the trunk. And the more variation you get, the more stressed the tree is. So here you can see the maximum daily trunk diameter and then the minimum. And then that MDS value is the difference between those two. So maximum daily shrinkage. And the larger that value is, the larger or the more that tree is stressed. But, there's always a but, it's not perfect. Because the bigger your trunk is, the more that shrink is going to be. It needs to be expressed as a relative to that overall trunk diameter. So if your trunk diameter is 10 centimeters, it's going to shrink much more than if your trunk diameter is 5 centimeters. So you need to take that into account. An absolute value is not good for every single tree or every single part of that block. So you need to get some sort of historical knowledge of what your block is already doing before you start looking at how can I manage that. And then the other thing that you can look at, especially in younger trees, is trunk growth rate. So that's the difference between one day to the next. So you're looking at that linear increase in trunk growth rate. So, and again, that's going to be a function of, or affected by the environment. Looking at temperature, humidity, wind speed, all that affects that trunk growth rate. So even though you might be managing your water correctly, environment can have a big impact on that. So for the trunk Andrometers, I talk about that maximum daily shrinkage. It's not perfect because you have big trunks and little trunks and they shrink differently. But also the shrinkage depends on the level of stress. So in mild to moderate stress, the shrinkage will increase when the tree is under more stress. But if you go beyond that and the tree starts to get into a severe stress, that shrinkage starts to decrease again because it's not able to recover. You don't get that recovery at night. So when you don't get that recovery at night, your maximum daily shrinkage might be small, so you might think your trees are not stressed, but they're actually very, very stressed. So relying entirely on trunk Andrometers is not a clear-cut solution. They're useful, but you really need to understand what's going on in your block and not entirely rely on what the data is showing you. Fruit growth, so we put these fruit sensors on. It's basically the same concept. It is measuring the diameter of the fruit. And so as the fruit grows, it'll continue to expand. And then you can also look at the daily shrinkage, but it's not as reliable. You generally focus on that daily growth rate when you're managing fruit. And it does work quite well, and we could see even in hot days where you're managing water perfectly that fruit growth rate slows. You kind of lose control over your ability to optimize fruit when it's really hot. You can't really do much about that. The other challenge with fruit Andrometers is their stability on the tree. They fall off, they shift a little bit. That slight shift affects all your measurements, so you need to be mindful of that. And then also, what fruit within a tree is so variable. How do you select 3 different locations within a small area of your block to actually represent what's going on for those thousands of apples in your block? And it's very difficult to do. And so it's really good to get your fruit growth measurements, and it's nice to get the data in real time. But I think it'd be a challenge to manage your irrigation based on 3 apples that you're measuring continuously throughout the season. So lastly, I just want to kind of go, where we're going from now. So this is some of the projects in the Smart Orchard are coming to an end. We're hoping that it's really going to be a dynamic process where new technologies are going to be tested in an orchard. We may not stick with the commercial block. We may move into a research orchard environment for long-term stability. Because actually the block that we're working in this year might be torn out at the end of this calendar year. So that's a reality working in commercial orchards. So we may move to the research orchard. We're going to continue to seek out new technologies and new strategies for data integration. And a big part of what we're moving towards now is integrating so I talk about layers of data and we have all this data from the soil, from the environment, we have spatial variability within the block, and then we have what's going on in the plant. From that, we're then working with a group that does a lot of artificial intelligence work, so they're a bunch of computer scientists, and they are working in the AI field. And the idea is that we can take all these really intensive layers of data that we've collected in projects like the Smart Orchard and develop better models. And that's really what it comes down to. So some of the cold hardiness models that we have for springtime for cherries are pretty rudimentary, same for grapes. Some of the sunburn models we have for apples, they're pretty basic. We have we have a pretty good idea of where the thresholds are, but there could be variability around that. And I think having these layers of data to integrate into this AI approach will help fine-tune some of those models and make them more useful and more reliable for the industry. So just lastly, talking about adopting sensors, and I like to include kind of some of this advice is there are lots of sensors out there. There's lots of sensors that are coming onto the market. You want to make sure you're getting something that's tested. You want to make sure that it's peer-reviewed, that very often some of the sensors aren't very transparent in how they actually measure what they're measuring. And you want to make sure that's good. And the other thing is be wary of data ownership. Data ownership is a big thing. Data is powerful, and having long-term knowledge of your blocks and how those trees are performing, how that yield is performing. Some of the companies out there are subscription-based. So before you jump into that technology and you get stuck in that cycle, and because you don't want to let go of that data, just be wary of what happens if you decide to step out of it. The other thing is universal data. So you want the sensors that can be integrated into different types of software. If it comes with their own software platform and that's it, if it's a really good sensor, it doesn't matter because you're going to use it because it works. But if you're not sure whether you're going to keep it and you're in the test phase, you want to make sure that it can be integrated into other platforms. It's really important. And then really it comes down to when you adopt something for not just in the test phase but into your operations is thinking about how does this data, because it could produce a really nice image of spatial variability, or it can produce a really nice graph of how that tree is performing day to day to day, but how does it lead to a decision that improves fruit quality or improves productivity long term? So just keep that in mind. So big thank you. There's lots of tools, lots of toys in the sandbox, and some are better than others. And we're just kind of hope to act as a filter for that going into the future. Thank you.